Well, now that we understand a couple of the non-idealities that can occur in real structures, what I'd like to discuss in this lecture is a measurement that is used widely to characterize real MOS structures. This is an analysis of the capacitance versus voltage characteristics of the MOS capacitor that we've been discussing. So the experiment would go something like this. We would have an MOS capacitor. We've been talking about how the bands bend and what happens in the semiconductor when we change the DC bias on the gate. We go from accumulation to flat band to depletion and then to inversion. Now what we're going to do is to add a small AC signal in series with that voltage. So we have both a DC and an AC voltage. And now we'll have an AC current that will flow through that capacitor. And that AC current will be the admittance of the capacitor times the AC voltage. So we can use measurements like this to deduce what the capacitance is at a given DC bias. So we can bias it in accumulation, measure the capacitance, bias it in depletion and measure the capacitance, sweep across the whole bias regime. So we'll be doing this, and for a typical MOS structure like this, just remind you that typical numbers are that we may have 1 to 2 nanometers thickness of SiO2, just to get us calibrated on what's real. So we understand how the DC bias affects the MOS capacitor. At flat band, there's no electric field, no band bending. Negative voltage on the gate bends the bands up. We say we accumulate the semiconductor. We pile up majority carriers at the interface. When we apply a positive voltage to the gate, we bend the bands down. We first deplete the P-type semiconductor, and then we invert the P-type semiconductor. So remember, I'm doing all of my discussion with a P-type semiconductor. You should think about this. What does accumulation, depletion, inversion look like on an N-type semiconductor? Right? All of the voltages are opposite. Now, we can think of this system as 2 capacitors in series. There is a capacitor due to the fact that we have 1 to 2 nanometers of silicon dioxide. So that's an insulator capacitance there. There is also a capacitance due to the fact that we've got charge in the semiconductor that's varying with voltage. So we have an oxide capacitor in series with a semiconductor capacitor. The thing about the semiconductor capacitor is it depends on the band bending in the semiconductor, so it depends on the bias that we apply. Okay, so what would an ideal capacitance versus voltage structure look like? Well, if I apply a negative voltage and I'm accumulated, then I have a metallic plate on top of the silicon dioxide insulator. I've got a large number of holes piling up right at the interface right below the silicon dioxide. That's like 2 metal plates around silicon dioxide. That's the capacitance of the oxide layer itself. So in the accumulation regime, the capacitance that I would measure in this structure is the capacitance of the oxide alone. Then, as we move the DC bias so that we bend the bands down and deplete, we now have a semiconductor capacitance. The semiconductor capacitance is the dielectric constant of the semiconductor divided by the depth of the depletion region. So the depletion region is depleted of carriers. It's acting as an insulator. Below the depletion region is a doped P-type layer that is sort of like a metallic plate. Now I have 2 different insulators between 2 metallic plates. I have 2 capacitors in series. The overall capacitance is going to drop as I deplete the semiconductor. As I continue to increase the DC bias, I will eventually invert the semiconductor. Now, we'll have to talk a little bit more about what goes on in inversion, but you'll recall that it is hard to bend the bands by more than 2 psi b. So that means there is a maximum depth that we can achieve in the depletion region depth. Once we've made the semiconductor capacitance as small as possible, then we have 2 constant capacitors in series and we have a lower capacitance in the inversion regime. Now, this happens to occur if I do the measurement at high frequency. We'll have to discuss this in a little bit more in a few slides. Okay, so how do we understand this? We can understand this in terms of what's happening to the charges inside the semiconductor. As I mentioned, in accumulation, we have a metallic plate that has a sheet charge on its surface, but we also have a semiconductor that is accumulated, so the accumulated whole charge is piling up right at the interface. We have the charge on two metallic plates surrounding the insulator, which is why we have the insulator capacitance in accumulation. In depletion, we have depleted the semiconductor to some certain depth. We have a metal plate at the top of the insulator. We have a metal plate underneath the depleted semiconductor. So we have two different dielectric materials inside between the two plates. The depletion region is typically much thicker, significantly thicker than the oxide layer. We have two capacitors in series. When you put two capacitors in series, the overall capacitance is going to drop. And then in inversion, we have pushed the depletion region depth as far as we can by bending the bands to psi b. And we also have a strong inversion layer. Now, you might ask, don't we have a metallic plate now? A strong inversion layer, lots of electrons, a highly conductive layer right on the bottom of this insulator, and a metal right on the top. Shouldn't we get the oxide capacitance again? Well, you do if you measure the capacitance at a low enough frequency. But if we measure it at a high enough frequency, and it usually doesn't take a very high frequency, what we find is that this charge cannot follow the AC signal. Because this inversion charge, these are minority carrier electrons. Where do they come from? They come through generation recombination processes in the p-type semiconductor. That takes some time. So if the frequency is high enough, the inversion charge just cannot follow the AC signal. As far as the AC signal is concerned, it's not there. The AC signal just sees the depletion charge. And the depletion, which stops growing, so we see this constant capacitance. Okay, now in a realistic structure, of course, we have to account for the metal semiconductor work function difference and any charges at the interface. So the flat band voltage will typically have a negative value in a p-type semiconductor. So we'll just shift the whole curve. We'll translate it to the left. So that's an easy shift to make. Now, I want to mention just once more about this issue about what happens when we're in inversion. When I measure it in high frequencies, it's as though the inversion layer charge was not there. If I were to measure it under a low enough frequency, however, then the generation processes that are needed to increase and decrease the inversion layer charge so that it can follow the AC signal, if the frequency is low enough, the inversion layer charge can keep up with it, then it would be as though I have two metallic plates around the insulator, and my capacitance would go up to the insulator capacitance again. So I would see a dramatically different capacitance in the inversion region if I measured the CV capacitance at a low enough frequency. So typically one has to be very careful in order to get low enough frequencies to observe this characteristic, and you would more easily measure the high frequency characteristic. So the point is that there is an awful lot of physics going on here that you can understand by doing these simple measurements on MOS capacitors. And that's why this has become such a powerful tool for people who are exploring these systems. Now, we should point out that we're interested in MOS capacitors because it's the heart. They're the heart of MOSFETs. So we've just been thinking about this MOS capacitor, but it is actually connected to a source and a drain. Now, if it's connected to a source and a drain, then what you would find is that if you had a transistor, and if it had a large enough gate so that it had a big enough capacitance that you didn't have to worry about all of the stray parasitics and everything, and you actually could do this MOS measurement on the gate of a large transistor, you would find that you always measure the low frequency characteristics. All right. Why is that? Well, that's because we have this source of electrons on both sides of the MOS capacitor. Electrons can move in and out as rapidly as they're needed for the inversion layer to follow the AC signal. So we could go to very high frequencies and still measure the low frequency characteristic of the MOS capacitor. So we would see a distinctly different MOS characteristic if the MOS capacitor were actually part of a MOSFET. So that's worth keeping in mind. So this can be a very powerful analysis tool. So for example, if we simply note the capacitance in the accumulation regime, that's just the capacitance of the oxide itself. Well, I could use this to measure the thickness of the oxide. And it is a frequently used way to measure the thickness of thin gate oxides. If I note the flat band capacitance, and it turns out if you do an exact analysis of the MOS system, you can compute what the flat band capacitance should be, and then you can read off the voltage that it occurs at. If it doesn't occur at 0 gate volts, and it never will, then you know that you're not dealing with an ideal system. If you know the metal semiconductor work function difference, and you probably do, then you could deduce how much charge there is at the oxide silicon interface. So that would be a useful thing to be able to deduce. If you go out to the inversion region, where the depletion region is now at its maximum value depends on psi b. Psi b depends on the doping density of the semiconductor. So by measuring this capacitance, which is the series capacitance of the oxide and the depleted semiconductor, I would be able to deduce what psi b and therefore what the doping density of the semiconductor is. So with these simple measurements, I could deduce things like thickness of the oxide, doping of the semiconductor, charge at the oxide silicon interface. So that's one of the reasons that MOS capacitors have been so extensively used to study these systems. I mentioned earlier that there are some complicated things. There can be charges in the oxide. There can be charges that change with bias when I do these MOS measurements. And all of those effects are explored by MOS-CB measurements of this kind. So it's a useful analysis tool. We can not only get some basic techniques, basic parameters that are important to us, but we can do some more sophisticated studies as well. All right, so let's just summarize. We won't really need to discuss CV measurements to understand how MOSFETs operate, but it's such a widely used characterization tool that we want to be aware of it. So let me just summarize what we've learned about CV measurements. We would expect a CV measurement to look something like this. Real structures display a non-zero flat band voltage, and we've understood the physics of why the capacitance is high in accumulation, why it decreases in depletion, and why it stops decreasing when we invert the semiconductor and reaches a constant value when we do the measurement at high frequencies. Okay. All right, and there are a number of useful things that we can pull off it relating to work function differences and fixed charge. We can read off of this. When the capacitance saturates and becomes constant, we know the threshold voltage of this MOS capacitor. So it's a useful tool. Now, the different regions of the capacitance are occurring because we're changing the DC bias. So the measurement works by beginning, say, with a negative bias. We would apply a DC bias to bend the bands like this. Then we apply a small signal AC on top of this, wiggle the bands up and down a little bit, measure that additional AC current and deduce the capacitance. And we sweep through from negative to flat band and then depletion and inversion characteristics. So we fix the DC bias to produce one of these band bending situations, and then we measure the corresponding capacitance. That capacitance helps us understand where the charges are in this MOS system. Okay, and the way to understand these systems is just to think about when I am biasing the MOS capacitor in this regime, DC-wise, and now I apply a small signal AC current, where do the fluctuating charges appear? And if you think about it that way, you can understand why the MOS-CB characteristic has this particular shape. Okay, so that's MOS-CB characteristics. Now we're ready to move on to the next topic. And we're really now going to begin to get ready to prepare ourselves to understand MOSFETs. We've talked about charge in the semiconductor. There's a depleted charge, which affects the CV characteristics. There's an inversion charge, which also affects the CV characteristics. When we talk about MOSFETs, the current in a MOSFET is carried by the mobile charge. The mobile charge is the charge in the inversion layer. Electrons in a p-type semiconductor, holes in an n-type semiconductor. So for the next 2 lectures, we're going to be discussing this mobile charge. The mobile charge depends on the surface potential. That's the topic for the next lecture. The surface potential is determined by the gate voltage that we apply. That will be the topic of the second lecture coming up. So we'll begin by trying to develop an understanding in the next lecture of how the mobile charge varies as a function of the surface potential.